You probably know that if space were expanding, it would stretch the wavelength of light, making it redder. But did you know stretching it in time would also make it redder? That's what we'll talk about today on Nonexpanding, Evidence for and Against the Expanding Universe, Episode 1, The Real Reason for Cosmic Redshift. Of the evidence for the expanding universe, we're going to focus on cosmic redshift and cosmic time dilation. To review, light is an electromagnetic wave with a wavelength, which is its distance in space between the peaks, and its period, which is the time between the peaks. It also has a frequency, which is how often it repeats, which is 1 over its period. By wavelength, say a 400 nanometer wavelength light was emitted, that'd be violet, and it's observed at 600 nanometers, which is orange. We can compute its redshift, z, by 1 plus z equals its wavelength observed over the wavelength emitted, which means z equals 0.5. Wavelength and frequency are inversely related. That means when wavelength goes up, the frequency goes down. By frequency, our violet light will be 750 terahertz, which is observed at 500 terahertz, our orange light. And now the equation is 1 plus z equals the frequency emitted over the frequency observed, which is again z equals 0.5. And because the frequency is going down, that means its period is going up. The time dilation is predicted by the expanding universe. As a supernova happens and it moves away, each photon has to travel farther than the one before it. So the time of the supernova, let's say this blue line here, when viewed from the origin, would be observed as longer, the red line. Supernova achieve a maximum brightness and then they diminish as time goes on. And for type 1a supernova, they do that fairly predictably. So the greater its redshift and distance, then the longer it should take for it to diminish. And that's what's observed. This is the Pantheon plus Shoes data that has a distance modulus and redshift. So mu is the distance modulus, and it's this symbol. All the slides here and all the animations and charts are made with JavaScript, so you can check out its source on GitHub. Its links are in the description. I should also note that time dilation has been observed in quasars, and that was just recently, last month. So, the time-dilated past hypothesis. If our observations include redshift and time dilation, then we can interpret that as the redshifted light is time-dilated light. And that just leads me to think, well, what if the past is time-dilated? What if time is stretched out? That would mean something like clocks speeding up as they get faster. It's a strange concept, and we'll talk more about that in future videos. But for now, we just need to assume that without time dilation, space-time would be Minkowski. And with time dilation, events are more spread out. So our observed time is this red line. To think about it, we have a measured time, which is red, and that's in t. And we have a Minkowski time in blue, and that's tau. And that has no time dilation. So that would be like taking the time dilation out of measured time. We can convert one to the other with these formulas, which are described more in a paper that's linked in the description. But that gives us a redshift luminosity distance relationship, and we can compute a distance modulus from that, and then compare that to the Pantheon plus Shoes data I mentioned earlier. So this is each dot represents a supernova, and the line here is at Hubble's constant, that's at h sub 0 equals 70 kilometers per second per megaparsec. To find the best fit, the best value to use for Hubble's constant, we can take the sum of squared errors for all the data. So that's basically the distance modulus in the data minus the distance modulus from the model based on the data's redshift. And here are formulas for that. And here is a JavaScript function which will calculate this, and you just have to pass it a value for Hubble's constant, h sub 0. If we do that over a range of values for h sub 0, what we're looking for is the smallest sum of squared errors, and we can see here that the hypothesis has 70.5 kilometers per second per megaparsec for Hubble's constant as its best fit. Now, if we do the same thing for the current standard model of cosmology, which is called lambda CDM, then we put that in the green line here, we see that they're about the same as far as fits go. Although lambda CDM's best fit is that Hubble's constant equals 73.0 kilometers per second per megaparsec. That might sound familiar if you've heard of the Hubble tension or cosmological crisis. Basically, you're trying to figure out how fast the universe is actually expanding, and as we see, the supernova data for lambda CDM suggests a value of 73.0 kilometers per second per megaparsec. The problem is that the Planck CMB measurements with lambda CDM give us 67.4, and that's just not a good fit for the data. Another way to measure Hubble's constant is by the reappearing supernova that shows up multiple times due to a gravitational lens. The value they got here is 66.6, and we can see the 73.0 from the SHU supernova data and the 67.4 from the Planck CMB data. Here, for reference, is 70.5, the time-dilated past hypothesis value. So let's summarize. Light redshifts when stretched in space, or when it's stretched in time. Time dilation is observed in supernovae and quasars, and the time-dilated past hypothesis says the past is time-dilated. Redshifted light is time-dilated light. Space is not expanding, and Hubble's constant is 70.5 kilometers per second per megaparsec. So, of the expanding universe evidence, we talked about the redshift and time dilation, but there's obviously more here to talk about, and we'll get to all this in a future episodes. Just let me know what you would like to hear about first. Leave a message in the comments, leave your criticisms, subscribe, but also check out the links in the description to the source code and the animations. I'd like to thank Bob for his input. Have a great day.